Okay, let's continue on. Question 13. Chris listed 4 chemical formulas and their matching chemical names in his notebook as shown below. According to Chris's teacher, he named only one of the components correctly. All right, let's look at them one at a time. And then it's asking which did he name correctly? SO2, and they wrote here sulfur oxide. So now, one thing to keep in mind, we want to notice whether it's an ionic compound or a molecular compound. If it's ionic, it's going to have a metal, and if it's molecular, it will not. Okay, SO2, sulfur, oxygen, not metals. If you're not sure, you could check your a periodic table. But when we have a molecular compound, which this is, because we can see that has no metal, we name our compound with those prefixes like di. So this should be sulfur dioxide. Okay, so that's named incorrectly. Here we have, this says carbon sulfide. Well, guess what? That's Ca, that's calcium. C is carbon. So that's just the wrong name there. So that is incorrect. Here we have nitrogen monoxide. So nitrogen is not a metal, nor is oxygen. So nitrogen monoxide. That seems correct. And here we have our first ionic compound, magnesium chloride. So magnesium is our metal. So here that should just be called magnesium chloride. We don't use these prefixes with ionic compounds. We just call it magnesium chloride. So magnesium dichloride is incorrect for a molecular compound. So our answer is nitrogen monoxide. Nitrogen monoxide. Number 3. Right, and then also should mention, might be useful for another question, that so for the first compound here, we don't use the prefix mono except for on the second of the 2 compounds. So we wouldn't call this mononitrogen monoxide. But if there were 2 of them, we would say dinitrogen monoxide. Okay, but in this case, we don't need to put any prefixes on nitrogen because that's a rule for molecular compounds that we only use when there's a single atom of something in the compound. We use mono, but only on the second one. But all the other prefixes can go on both. So again, for example, if we had, I'm not saying this is an actual compound, but if it were, we could call that dinitrogen monoxide. But as it is, it was just NO, so it's nitrogen monoxide. But we don't say nitrogen monoxide. You just don't do that. Okay, next. Question 14. Which of the following statements accurately describes the reaction above? We've got, looks like hydrogen and chloride, so a hydrochloric aqueous solution. Then we have H2, hydrogen gas, and chlorine gas being produced. So which of the following describes the reaction above? Let's check the first one. Combining hydrogen gas and chlorine gas produces hydrochloric acid. The direction of this arrow is important. Okay, so this is not just like an equation. This is telling us we started with this and we ended up with that, right? This would be like our reactants, and these are our products. Okay, so it's going this way. So we didn't combine those to get hydrochloric acid. It went the other way around. We started with hydrochloric acid, and then we got these 2 gases from it. So that's incorrect. Combining hydrochloric acid with hydrogen gas produces chlorine gas. Well, no, we're not combining hydrochloric acid with anything. It's just there by itself in this chemical reaction. Hydrogen gas is produced when hydrochloric acid is combined with chlorine. Again, the hydrochloric acid is not being combined with the chlorine. In fact, it's not being combined with anything. A lot of times we have something plus something mixes together and gets something else. But in this case, that's not happening. Let's look, what does D say? Hydrogen gas and chlorine gas are produced when hydrochloric acid is broken down. Okay, so that makes more sense. First of all, the first clue is produced. Hydrogen and chlorine gas are produced because they're products. So they are produced from this breaking down. But it's super important to notice the arrow, right? This is what's being produced. It's a product, it's being produced. So how is it breaking down? Maybe just naturally, maybe it just evaporates, maybe potentially if there's it's being warmed, these components would, well, if we added heat to it, it would probably just happen quicker, right? We know that heat is a catalyst for reactions. It speeds up reactions, but yeah, it's just breaking down and gases evaporating to the air. All right, so next question. Numbered patterns in the periodic table. Identify the row that correctly describes the patterns in the periodic table above. All right, let's look at the first one. It's saying we're either talking about, is this guy either a family or a period? A family, or another word for family, the word we were using this year was a group. So groups are the ones that are vertical, these columns. These are groups, and these different elements have similar properties when they're in a group. So one is definitely a group. So now we know that we can rule that out because that's not correct. A period, however, is anything that's in the same row. Okay, we call that a period. So we have a family and then a period next. Okay, so we're still could be either of these two. What's next? 3 is either going to be nonmetals or metals. So everything to the left of this staircase line here are pretty much metals. There are some metalloids that are kind of in between here, but the majority of everything here are metals. So we would go with metals here. Then that leaves this being nonmetals, and that is the case. These are nonmetals generally, except maybe some metalloids in this area. These are generally nonmetals, so that gives us answer B. Okay, a student dissolves sugar in a beaker of water. Individually, the water and sugar are classified as, our choice is either compounds or elements. So they're definitely compounds. Sugar is made up of a variety of different elements, and so is water, hydrogen and oxygen. So we know they're compounds, so it's going to be one of those two here. And the combination of both, so sugar and water, is either a mechanical mixture of solution. Well, it's a solution because it dissolves into the water and it appears to be a liquid, even though there are sugar molecules in the water. Mechanical mixture, if it was a mixture, we would see the sugar floating around. It would be mixed in, but it would be in there, but it would be visible. It would not have dissolved into the solution. Okay, next one. The information on the above shows that a fluorine atom has how many electrons and how many neutrons. So electrons, this is our atomic number. This tells us the number of protons, also the number of electrons, because in a neutral atom, which we assume all these on the periodic table to be, They're not, we don't assume them to be ionics or ions where they've lost or gained electrons. So protons and electrons must be balanced. So there's the same number of electrons. So we know it's one of these two answers. And how many neutrons? Well, our neutrons will be equal to our atomic mass minus our atomic number. So if I have an atomic mass of 19 or 19.00 minus 9, then I have 10 neutrons. Okay, 10 neutrons. So answer is A. Combustion and corrosion are similar reactions because they both, answer is, requires oxygen. So if you recall, we did a portion during this unit on reactions that involve oxygen, and they were combustion, rust was another one. We also had cellular respiration, which is how the cells break down like sugar molecules and turn them into energy for the body, ATP, and it also involves the use of oxygen. What else? What was the other one? I'm forgetting one right now. Combustion, rust, cellular respiration. Luckily for this question, we don't need to list them all, but anyway, combustion and corrosion. Sorry, rust is the result of corrosion. Rust is from corrosion. So combustion and corrosion are similar because they both require oxygen. Have metal as a reactant. Corrosion does, but combustion doesn't. We could burn wood. We're not typically burning metal. Release oxygen as a product. Well, combustion releases carbon dioxide, not oxygen. It consumes oxygen. And release carbon dioxide as a product. Well, combustion does, but corrosion does not. Okay, they do, however, both use oxygen as a reactant. They both they need oxygen to do their process. Okay, so that's 18C. Next up, when magnesium metal is placed in hydrochloric acid and hydrogen gas bubbles are produced, which of the following combinations of reactants would have the fastest reaction rate? So we've got our hydrochloric acid and our magnesium. In this case, we've got 5% solution and we have these metal strips. In B, we've got a 5% solution again, but we've got magnesium metal powder. So we talked about things that affect rates of reaction, and they were things like concentration. Okay, if we have a high concentration of a chemical, that can increase the rate of reaction because there's more of those molecules to react. So the reaction is going to happen faster. And more surface area was another one. Okay, so when we have this metal ground up, if it's the same amount of metal, but it's ground up, it has more of, each piece has more of it exposed to that solution, right? As opposed to if we have it just in one big piece, the solution can only get at the outer layer of this piece of metal, whereas the solution can get at all these parts of that metal. So there's more surface area exposed. Okay, so that's going to also increase the rate of reaction. So B is definitely already going to be faster than A. Now we have here a 10% hydrochloric solution. So that was the first thing I mentioned, concentration. So a higher concentration is good. Now, which one would be faster between these two? That is kind of hard to say. I would tend to go with the metal powder because I think it's just the way it's ground down. It's going to be so much more exposed. But it's honestly not something we can really know from this question. But D has both of those things. It's got a higher concentration, plus it has more surface area exposed. So the reaction is going to be a lot faster on D. Okay. In a science demonstration, a teacher combined fluorescent dye, hydrogen peroxide, and a chemical called CPPO. The resulting solution produced heat and a bright green glow. Which type of reaction did the teacher demonstrate? If we look at our options, well, the first thing that jumps out to me is these two choices, endothermic and exothermic. Well, when we produce heat and if something feels hot, we know it's exothermic. So it's definitely not endothermic. Didn't say anything about anything burning, so combustion is not correct. Corrosion, that's rusting, and that's also a very slow reaction and doesn't sound like this reaction at all. So definitely exothermic. Next one. Use the following information to answer numerical response. Question 2. We have 3 substances labeled substance X, Y, and Z. And it tells us it either conducts electricity, yes or no, and is it a gas, solid, or liquid at room temperature? And asks us to classify the above as ionic or molecular using the following code: 1 for ionic, 2 for molecular. The big giveaway is mostly that it conducts electricity. So ionic compounds have metals in them, so they have the ability to conduct electricity. So Y is going to be ionic. And the other that do not conduct electricity are very likely not ionic. So we're going to label those as molecular. um, and also an ionic compound here. It's a solid. And these two are either gas or liquid. So the ionic compounds are often solids. So we also, that's another clue. But honestly, right here, it's the main tip off. Okay, substances that biodegrade are often considered green products because they have a low impact on the environment. Information about 5 waste products is listed below: a plastic ring, aluminum cans, plastic shopping bags, orange peels, and paper. And they're either recyclable. And are they toxic? This one we don't know. This one is not toxic. This one we're uncertain. This is not toxic, not toxic. Okay, so there's some information about those. What else do we have? We have another thing here that says what shows the different products on the left, and then over a period of years, the time it takes for them to biodegrade. So plastic ring holders for cans take 450 years to biodegrade. Aluminum cans 100. Plastic shopping bags would take around 40 years to degrade. Orange peels and paper looks like less than a year. And in this zoomed in model, we could see that orange peels take about 6 months and paper is about 5 months. Okay, so now what are they asking us? Aluminum cans and the plastic ring holders should not be considered green products because they. So let's look at, what is it? Aluminum cans and plastic ring holders. They said they should not be considered green. So we're looking at these 2 products. Now, they are recyclable, so that's a good thing. We don't know if these are toxic. They may or may not be. And then this one is definitely not toxic. So far, they don't look so bad. But when we look at the number of years it takes them to biodegrade, they take a very long time. So in an ideal situation, these are going to be recycled and there's not going to be any problems from them. However, if they are not, or they make their way into places where they shouldn't be, like into oceans or on land and not into proper disposal places, that's going to be a problem and they're not going to go away very quickly at all. So answer is that they take too long to biodegrade. A says may produce toxic waste, should not be considered green. Now, that's true of the plastic rings. It was uncertain, so it may produce toxic waste. However, we're talking about both of these, right? We're also talking about aluminum cans, and aluminum cans do not produce toxic waste from that chart. Can be recycled and reused. They both can be recycled and assumingly reused. But that's not a reason why they would not be considered green. It's a good thing. That's not a reason for them to not be considered green. And they take up too much space in landfills. I mean, if they make their way to the landfill instead of being recycled, I mean, I don't know if they take up all that much space. Crushed aluminum can. This one's a little bit kind of like iffy. I would tend to say no for that. But the most obvious answer, which the information above is trying to point us towards, is that they take a very long time to biodegrade. Okay, and that's the main problem because, we don't want them in the landfills either, and they'll be there for a long time. Okay, in an experiment, students planted 3 groups of seeds from the same species of plant. All 3 groups of planted seeds were grown under identical conditions except for the concentration of fertilizer applied. The average height of the plants in each group was recorded after 5 days. So here we go, average height of plants after 5 days. And this is the concentration. In one case, they had a low amount of fertilizer, then a medium amount, and a high amount. So at a low amount, they grew 3. At a medium amount, they grew even better, 5. And at a high amount, they did not grow very well at all. According to the data above, which of the following graphs models the relationship between plant growth and fertilizer use? So we can see that at the beginning, a lower amount gives a low growth, and then adding more fertilizer gives a growth. So, and let's look at our graphs here. We have plant height and concentration of fertilizer. So this would be like the low, the medium, and the high concentration. And here we have a low plant growth, yes. Then medium plant growth. That looks so far correct. As we put more plant fertilizer, the plant is growing higher, but then at a high rate, it's saying it stays the same as medium. That's not true. It drops off, right? It gets lower. So this looks better. Here's our low, our medium, and our high. At a lower, it grows only a certain amount. At medium amount, it grows better, but then at a high amount, it's too much and the plant does not do well. Okay, so B is much better. Again, this low, that starts okay. At medium, it's saying it's dropping, which is not the case. And at high, it's saying it's getting even better, which is also not the case. And yeah, we could go through the same reasoning for these ones, but B is the correct answer. Okay, let's do a couple more and then we'll end this video. The graph below shows the death rate of mosquitoes that are exposed to different concentrations of pesticide. So at 2 parts per trillion, which is a lower concentration than 2 parts per billion, the T means trillion, B billion, and then 2 parts per million, which is an even higher concentration. Remember, we talked about this in the other one. So 2 parts per trillion is a lot, right? So if there's 2 in that many different, that total of molecules, that's very dilute. But now we have 2 in 1 billion. That's still not very strong, but it's stronger. There's 2 for every billion instead of trillion. Then 2 for every 1 million. Well, that's even more concentrated, right? And if we kept going, if I said 2 in every 10, well, that's lots. 2 in 1 million, not a big deal. 2 in 1 billion, even less of a big deal. 2 in 1 trillion, definitely not. Does not sound like a big deal. So yeah, so our concentration of pesticides from left to right is going from low to high, right? Call that low, medium, high concentration. And this is how it's being affected. Death rate of exposure after pesticides. So at the low concentration, this is the death rate. At the medium, here's the death rate. At the higher Concentration here is the death rate. And the variables of the investigation were the type of pesticide, the pesticide concentration, death rate of mosquitoes, and method of application. The graph below shows the death rate of mosquitoes that are exposed to different concentrations, right? So that's what we were changing. We were changing the concentrations. So in the investigation that generated the data for the graph above, two controlled variables are numbered. So controlled variables are the ones that don't change. Okay. Those are things that we're making sure do not change. And the type of pesticide did not change. And the concentration did change. The death rate of mosquitoes, that's the result. That's the responding variable. Not that. And the method of pesticide application is also the same. So they applied that in the same way. The thing that changed was the concentration. So 1 and 4 are controlled variables. They're the things that don't change. The pesticide concentration did change, and death rate of mosquitoes is the result, right? That's our responding variable or a dependent variable. Okay, last question, last page. We'll do these two and get you guys halfway there. All right. So we've got this diagram, and it says use the following information. We've got essential organic nutrients, organic nutrient 1, 2, and 3, and it describes below. This one used as structural molecules. This one is used as a source of natural oils and stored as fat. And these are used for energy for metabolism. So we're talking about carbohydrates, fats, proteins, that kind of thing. So we've got the nutrient that fits into space number 2. Okay, oils and fats, the way we call oil and fat in science is lipid. So it's a lipid. Okay, protein would be this one, structural molecules, and these would be carbohydrates. And these are lipids or fats. Okay, use the following information to answer question 25. A researcher determines that the mercury levels in a river decrease as the water flows downstream from a factory. The decrease in the mercury levels is most likely a result of dilution. So dilution is how could I explain that? It's the the lowering of concentration of something in a liquid. Okay, so in this case, we've got mercury is in the river, and as it moves down the river, it gets dispersed essentially. But because it's in water, that type of dispersion we call a dilution. So it's diluting the further it goes down, and the more it gets mixed in with more and more water. Okay. Let's try to finish up to question 30. Question 26. Which of the following substances is organic and can be produced by plants? So remember, organic has to have carbon and hydrogen. If they don't have both, it's not organic. Doesn't have both, doesn't have both, does not have both. Oxygen doesn't have either. So sucrose does have both of those. Plus it has oxygen as well. It's made of carbon, hydrogen, and oxygen. There you go. Next one, DDT concentrations in a marine food chain. So the plankton have 15 parts per billion, squid have 22 parts per billion, tuna 43, and the shark 5,200 parts per billion. The information above best illustrates biomagnification, right? So the concentration gets higher and higher the further up the food chain we go. And that effect of the toxin gets magnified as it accumulates in the higher tiers of the food chain. Okay, For students, statements about the pH scale. Student 1, 2, 3, and 4. Student 1 says acids have a lower pH than bases. That's true. Bases are located at the beginning of the pH scale, starting at 1. That's not true. An exactly neutral substance has a pH of 7. That's true. Weak bases have the highest pH value. Let me read that one again. Weak bases have the highest pH value. No, the highest pH value would be strong bases, so that's not true as well. So which two students provided statements that are correct? So that would be student 1 and student 3, and here we've identified that. So yeah, so number 4, weak bases have a high. So this would be scale 7, 0, 14. The highest pHs are up here, and those are the strongest of bases, so not the weakest, right? So that's wrong. Yeah, and we already went through this too. Bases are located at the beginning of the pH scale. Nope. Okay, next one. We have water samples, 1, 2, 3, and 4. We have dissolved oxygen. No, weird. Okay. Didn't think I could erase those, but so and ask which water samples would support the greatest diversity of organisms. So hopefully we recall that water that is more close to neutral is the best. And they're asking us to make two choices, so we're looking basically for the top two. So something that has a neutral water is good for diversity of life, supports more life. And the more dissolved oxygen it has, the better too. So this has both the highest dissolved oxygen and the pH that's closest to neutral. In fact, it is exactly neutral. So that would be a very good environment. So if we have to pick two, let's look at the next best option. So this one has the next best level of dissolved oxygen, and it also has the next best level of pH. It's a little bit acidic, but not too bad. Oh, and there was also phosphorus. Okay, we don't want to have high concentrations of this. So this had a low concentration of phosphorus. So this really was the ideal water. This has a lower pH and a lower dissolved oxygen, but still not too bad. It does have high concentration of phosphorus, which is not really good. But if we're having to pick the best, the water samples that would support the greatest diversity of organisms, these are the best two choices. So that would be 2 and 4. So that's why we had answer C. And here we go. Last question before we take a break. After the Exxon Valdez oil spill on March 24th, 89, the oil was tracked as it moved from the site of the spill to the surrounding environment. So it started off here at day 4, it spread to here, day 7 here, 11, 14, so on, so on, so on. 56 days, it made it all the way down here. The question, the movement of the oil through the water to different locations around the spill represents dissolving, deposition, degradation, or dispersion. So this is being spread out along the coast. So we're going to go with dispersion for this one. Notice if we were talking about in the previous example, we said when mercury was in the water, we used the term dilution for something that's in a liquid, but we didn't have that option here. But dispersion is definitely happening here. This is being spread out. Dispersion is a more general term when something is spread out. And this oil really, I don't think is not exactly dissolving into the water. It's not diluting, it's just spreading out. So it's dispersion. Okay, and just as a reminder too, remember this answer key. You can always check these answers at, in this case, it was at the beginning. What question was that? Question 30. So let's go find it. these are where the solution, the answer key answers are. So 30 was here. A, 30A, same as we said, dispersion. Okay, perfect. All right, so we'll continue on here in the next video.